Good morning, everyone. Hello. I'm Vinayak Saokar, VP of Engineering at Exabeam. This is Arun, who is the technical lead driving the integration for ClickHouse into the SecOps platform. So we are very excited to share how we leveraged ClickHouse basically to scale the Exabeam security operations platform. Before I start, I just want to thank Shri from ClickHouse. So he was very much helpful guiding us technically across along this process. I know he's here somewhere. So this is what we'll cover. I'll just give an overview of the platform itself, which will help us understand why we need a real-time analytics database in cybersecurity. Then we'll also do a deep dive into the scale metrics. So we have this live in 10 global regions, and we'll share some metrics along this for ClickHouse instances. And Arun will walk us through the high-level architecture, including how we optimize ingestion to handle million events per second, and also how we optimized the search for faster performance. So these are basically the 4 pillars, right? So we leverage AI and machine learning to deliver end-to-end threat detection, investigation, and response. And on the ingestion pipeline, we support aggregating data across different sources, including cloud workloads, your SaaS applications, endpoints, firewalls, and more. So this pipeline basically enriches the data with additional context so that we can use it during the threat detection. And we currently support around 9,500 parsers. So the second pillar is the threat detection. So this is the engine that leverages AI and machine learning, and we deliver user and entity behavior analytics, prioritization, risk scoring, and correlation. So this is where we can surface real threats quickly while minimizing noise. So here we have around 2,000 analytic rules and also 750 behavioral models currently in production. On the investigation side, we provide event timelines. So you can look at the events in terms of the timelines, and also what we call AI co-pilots. We have generative AI co-pilots that give you threat summaries, right? It'll take all the detections and run through generative AI and give you a nice deep insight into the threat. And lastly, on the response side, so we have an automation platform so that lets enterprises automate their playbooks, so based on the third-party tools they could integrate with. So this sort of gives you a context why we need a real-time analytics database, right? So one key metric in cybersecurity is mean time to detection, which means the time the events come in and the time we detect the threat and show it to the security analyst. That's very key. So it needs to be very performant, and that's where ClickHouse has helped us to meet that, what we call MTDT, mean time to detection, to be a lower number. So some metrics I want to share. I want to go through each of them. But we, like I said, 10 regions across the globe, we leverage ClickHouse Cloud. So at peak, we are able to support 1.2 million events per second, and almost 80 billion events ingested daily. And so far, we have ingested 3.5 petabytes in the last few months alone, and growing. We have normalized the data into what we call a common information model, which 1,000+ fields. And this is the ClickHouse data model is built around that. And we let customers also add additional fields to that. So ClickHouse supports that in a multi-tenant format. And we are ingesting terabytes of data on a daily basis. And lastly, the hot search, what I said about mean time to detection is very critical, is to say, like, I want lower cost, faster queries so that I can do the detections and surface it to the security analysts. So I'll hand off to Arun now. So we'll do a deep dive on the technical architecture. And
thank you, Vinayak. So to handle 1 million events per second in our ClickHouse cloud, we did several optimization, and majorly, right? Like we utilize ClickHouse compute functionality to separate out write, merges, reads, because there are certain workloads are very read heavy, which should not affect the writes and merges. So this is how our typical high-level architecture might look like. Ingestor service will ingest the data into write instance. Write instance will specifically focus on writing the data into the ClickHouse. And merge instance will do the background merges. And read instance handle and serve the different read workloads. And we utilize ClickHouse management service to manage the schema in the ClickHouse environment. And again, one more optimization that we did is like utilizing consolidated field. So when searching one column, took sub-second response. And if you are searching for 180 plus columns, it provides like 8 plus seconds for a response. So we have like 1,200 plus columns, right? Like if you are fetching all the 1,200 plus columns, it might not be performant enough. So what we did is, while fetching the data, we try to fetch one single column, but individual predicates, or whenever query is applied, that will be applied on the individual columns. And another optimization is, right, like if this might be the hypothetical table with 1,200 plus columns, but if we are going with this particular model, which might not work well for ClickHouse because it has to sort more columns, and sorting and like merging, it takes a lot of time, and it might be computationally we need to add more hardware. But what we did with that approach is, right, try to reduce and optimize the fields. For example, right, if you see column C is specifically null, and like there will be like 80% of the columns in the model might be null. So we try to compress them and put it in certain rare fields, or these fields will be like key will be the column name and value will be the column value. So using this particular approach, we shrink the column from 1,200 plus columns to 250 columns. Again, the benefits of this particular approach is, right, like from 100K events per second to scale the ingestion up to 250K events per second on a 3-node cluster, 3 replica ClickHouse instance. That's the performance benefit that we gain with this particular approach. Again, one more optimization is, right, rare column names are indexed with the rare fields. So for example, whenever column B occurs with Bloom filter, right, it can identify the respective granule and it can fetch the result faster. And again, scaling the ingester. So to scale the ingester, we did several optimization. One is like to utilize gzip reader, which produces like 20% performance benefit on reading the files from the GCS buckets. And another optimization that we did is JSON to Jackson migration, which provides like 60% faster performance on data processing and JSON event processing. And again, we did one more optimization is like data writer optimization. So how quickly I can send 100K events through the network from my machine to ClickHouse. So initially we went with row binary format with the default with the JSON, and it took like 20 seconds to transmit the data through network once the data enters the data writer. But the main problem with the approach is, right, like it has to convert the data, JSON data into bytes, which took plenty of time. So the next one, what we did experiment with is utilize multiple threads and convert every row into bytes before sending to the data writer, and use binary stream utils to send the data to ClickHouse, which took 5 seconds to transmit the data through the network. And again, one more optimization is like ClickHouse recommendation is like utilize iterable byte array input stream to transmit the data. Again, we already convert the rows into bytes, transmit to the network, and which took like 1 second, but it took like pod memory of like 7 GB. When we investigated it, it utilizes iterator, and due to iterator, it is not eligible for garbage collection. And we made a wrapper around that to eliminate the iterator approach so that it can be eligible for the garbage collection immediately. And again, this particular feature is already available in the ClickHouse right now as a byte array queue input stream. But again, before this is how the before and after performance improvement. Before it was utilizing like around like 7 GB. After that, it was like around 4 GB. And before it was like 16K events per second. And after making this optimization, it was going up to like 20K events per second from the pod. When we went with ClickHouse in production environment, we encountered max pod file issue. The main problem that is, right, like when we insert 100K events as a batch, it is inserting data into multiple partitions. If due to inserting data into multiple partitions, it try to commit the data partition by partition, which occupies certain memory, and due to the memory, it utilizes high memory. Due to that, also, right, multiple pod file is also getting created. If you see the recent partition, right, if we emit 100 data, 95% of them go to the recent partition, and around like 3% go to the previous partition, and rest of the 1% share might go to like 27 different partition. Again, if you are writing into multiple partition, it will create multiple pod file, which is not optimal because ClickHouse has to merge this pod file, and it has to work on it. And due to that, merges will be scheduled, and if writes occupies high memory and merges also getting scheduled, merges will be aborted due to memory issues. So what we did to solve this particular problem is, right, from the pub/sub topic, we will get real-time and backlog events. Real-time ingester will send the backlog events to backlog topic and commit the real-time event into ClickHouse DB and acknowledge. Backlog ingester process at much bigger batch and reduce the number of pod file for the older partitions. Using this approach, it reduces the max pod file and also reduces operational cost with ClickHouse. Again, this is how it might look like with the real-time events and backlog events. Even the small percentage share of backlog events could create multiple pod file, which we avoided. And again, one more operational challenge that we encountered is when we went with ClickHouse in production, we went with n-gram index. N-gram index, it helps in regular expression cases and IP searches. Again, it requires more hardware because ClickHouse need to do background matches. Every background match, it has to recreate the index. Index could be expensive in our case due to the log data. So in order to avoid the hardware cost on the ClickHouse, what we did is we went with the tokenization approach, which tokenizes the data, which is very less tokens compared to the n-gram index. If you see like the huge text, multiple tokens will be generated, but tokenization is much preferred approach, which occupies less hardware, and it also improves the ClickHouse performance in terms of reduced index sizes. And again, regular expression is just like 1% of our customer query, so which is not a big concern for us, and we went with the tokenization approach. By leveraging ClickHouse, and Exabeam can able to deliver high speed, high scalable, low latency, and cost-efficient search capabilities.